All right, hello everyone. So one of the final FRQ questions that we're going to be discussing before the AP exams is this one that has a lot of questions in the topic of rotational motion, which for a lot of students can be one of the more difficult units. So I will try to cover all of the main ideas that turn up in this problem in sufficient detail. So to start with, we're looking at two pulleys, A and B. They have identical mass and radius, but one of them, pulley A, is a solid disk, and pulley B is really just an outer rim with a few spokes. So most of the mass of pulley B is concentrated on the far outside edge, and for pulley A, the mass is spread more throughout the center. So before I go into this problem, I want to remind everybody of a demo that I did in class. So you may remember the red and blue wands that we had, and we did a little demo where people were attempting to rotate these very quickly. So if you remember, what ended up happening with those rods is that the blue one had masses all the way out at the far edges, whereas the red one had two weights very close to the center. And that made this one very easy to rotate, whereas the blue one was much more difficult to rotate. So this was sort of our introduction to this concept of moment of inertia or rotational inertia. So the idea here is that the red beam has a, moving things around here. The red beam has a much lower moment of inertia, so it's easier to rotate. The blue one has a much higher moment of inertia, so it's more difficult to rotate. So the first question you're given is if we attach two spring scales to these pulleys and pull down on these strings with equal force, which pulley will complete a rotation sooner? So that's like saying if we took these two beams and rotated them with the same amount of torque, which one would complete one rotation sooner? And the answer is it's the one that's going to be easier to rotate. So in this case, pulley A has its mass concentrated on average closer to its center than pulley B does. So pulley A is going to complete a rotation sooner. And as a justification, we can say that the moment of inertia for pulley A is less than the moment of inertia for pulley B, so it's going to be easier to rotate. All right. So for part B, they want us to actually calculate the time that it would take this thing to rotate. So this is a rotational kinematics equation. So the linear analog to this question would be if an object is pushed with a constant force, how long would it take it to travel a certain distance? And the equation we would use for that would be this one that says displacement is equal to initial velocity times time plus 1/2 times the acceleration times t squared. The rotational equivalent of that equation will be this. The angular displacement is equal to the initial angular velocity times t plus 1/2 times the angular velocity times t squared. Now these pulleys start from rest, so we can actually get rid of this term. So this is the equation that we are wanting to solve. All right, so on the left-hand side, that's the angular displacement. If we're solving for the time that it takes to complete one revolution, that's an angular displacement of 2 pi radians. So I say 2 pi is equal to 1/2 alpha times t, and I'll call it ta now, squared. All right, so what is the acceleration? So we have to use another one of our rotational equations here. For linear motion, if we want to know the acceleration of an object, if we know the mass and the force acting on it, acceleration is equal to force divided by mass. The angular equivalent of this equation is that angular acceleration is equal to torque divided by moment of inertia. Right. So the torque in this case is equal to the force applied from the spring scale multiplied by the radius of the pulley. So that's Fs multiplied by Rp, that's what we're calling all of these variables, and then we're calling Ia the moment of inertia of pulley A. So we plug that into this equation here, and we get 2 pi equals 1/2 times Fs Rp over Ia times the time squared. All right, so if we rearrange this, we get 4 pi times moment of inertia over force times the radius equals time squared. And finally, the time is just going to be the square root of all of this. All right, and then there's a part 2. Is this answer consistent with your answer to part A? Answer that is yes, because if we look at this equation here and we sort of mentally subtract out everything that's a constant, the 4 pi is a constant, the force is the same for both pulleys, the radius is the same for both pulleys. So we can say for part 2, the time is proportional to the square root of the moment of inertia. So that tells us a pulley with a lower moment of inertia will take less time to rotate, which is what we said in part A. All right, so hopefully you're still with me. Let's go on to part C. All right, so part C introduces another pulley. Well, no, it's still pulley A, but now we are replacing the spring scale with a mass M. And the question here is to describe how the net torque and the angular momentum of the pulley will change over time if we just release this mass from rest. All right, so really 2 questions here. Oops, sorry. We have the net torque, which is going to be unchanged, or I guess the way they phrase it is not changing. And then the angular momentum. Remember, angular momentum is just sort of the rotational version of momentum that's going to be increasing. All right, so what's our justification here? So the net torque is going to be equal to the tension in the string, so whatever this force is, multiplied by the radius of the pulley. Right. And neither of those 2 values is changing, so the net torque is not changing. The angular momentum, if you remember the formula for regular momentum, that's mass times velocity. So this would be moment of inertia times angular velocity. The moment of inertia of the pulley is a constant, but the angular velocity is going to be increasing, so the angular momentum is going to increase as well. Another way you could justify it is that the torque acting on the pulley is going to be in the same direction as the rotation as it starts going. So that's analogous to saying if you push an object in the same direction that it's already moving, it's going to speed up rather than slow down, so its momentum is going to increase. All right, by the way, notice when I wrote this equation for net torque, I did not put the weight of the block in here. This the tension in the rope is not equal to the weight of the block. So this can be a common mistake. I want to make sure everybody understands this. The block itself is going to be accelerating downward, which means the forces acting on the block are not equal. So the weight is the gravitational force that's pulling down on the block. The rope is going to pull up on it with some tension force. If these 2 forces were equal, then the block would not accelerate. But since that's not what's happening, the block is accelerating downward. That means mg must be greater than the tension force. So the force that's actually causing the torque in the pulley is not equal to the weight of the block. It's actually going to be a little bit less than that. All right, so it's just an important side note there. All right, so finally, we look at part D. We have yet another figure here. So now we have a third pulley, pulley C. And for this one, you notice the string starts to unwind noticeably and get closer to the center of the pulley as this spring scale is pulled down. So now that's sort of the key difference between this pulley and the previous 2. And we are asked now to describe what happens with the net torque and the rotational kinetic energy of this pulley as time goes on. All right, so before, remember, we said the net torque was equal to the force of tension in the string multiplied by the radius of the pulley. And really, the radius that we are dealing with is this radius here, from the center of the pulley to the place where the string is. So if you look at these two pictures, that radius is getting smaller over time as the string unwinds. So since the radius is getting smaller, the torque, which is equal to the tension multiplied by that radius, I'll just call it R this time, that is actually decreasing. And the reason is because R is decreasing. The rotational kinetic energy, however, we are still applying a torque to this wheel in the same direction of rotation, so it is going to continue to speed up in its rotation over time. So the kinetic energy of rotation is going to increase as long as the spring scale is falling. Right. And again, we can give the same justification as before. The torque is in the same direction as the rotation. So again, the idea is if an object is just moving in a straight line, if you push it in the direction it's moving, it's going to speed up. If you push it in the opposite direction, it's going to slow down. The same thing works with torque and rotation. If the torque is in the same direction of rotation, the object will speed up. If the torque is in the opposite direction of rotation, then the object is going to slow down in its rotation. All right, so I think that does it for this problem. If you have any questions, please message me. Otherwise, thank you for watching.